In this video, we're going to introduce Newton's method, which is a way to approximate a root of a function. It can also be used to estimate when two functions are equal to each other. One of the main reasons this is useful is that it converges very quickly, but one of the reasons we'll study this also is because it's one of the few times we see an iterative process in calculus, but iterative processes show up a lot in mathematics and other areas that use math, so it's good to see at least one example of such a function. So let's get started on what we want to do. So let's say we're given a function y equals f of x, and we want to approximate a root of the function. So in other words, we r with f of r equals 0. So for instance, if we were thinking of this in terms of a graph, we might have our function looking something like this, and then this value here would be the r we're looking at. So now what we can do with this is what we're going to do is we're going to use the tangent line to approximate this. So the first thing we're going to do is we're going to start with a guess, and we'll call that guess x1. So some books will refer to it as x0, some as x1. It doesn't so much matter, it's just going to be the term that starts our process. So if we think of this above, we can just pick some value r1 that's going to be our guess, or x1 that's going to be our guess. So say this is our guess, then we go up here and we create the tangent line at this point, which we know how to do. And so this is our tangent line. And where this hits is going to be our second guess. So this will be x2. So let's go ahead and figure out a formula for x2, and then we'll see how to continue this. So the tangent line at the point x1, f of x1, we've seen this a lot this semester. This is y minus f of x1 is equal to f prime of x1, x minus x1. And now for our guess here, note we want when this line intersects the x-axis. So our second guess is when the tangent line intersects the x-axis. So let's figure out what that is. So that would mean our y is equal to 0. So I have 0 minus f of x1 is equal to f prime of x1. And now I'm calling this value x2. So we'll plug in the x2 there for x. And now I'm interested in figuring out what x2 is, so I want to solve for that. So if I divide both sides by f prime of x1, so this assumes that f prime is not 0. This is x2 minus x1. So then isolating the x2, I get x2 is x1 minus f of x1 over f prime of x1. And this is as long as f prime of x1 is not 0. If f prime of x1 is 0, then we're going to need to choose a different x1 as our guess. So that gives us our second estimation. So let's figure out, okay, well, what would we do then? Let's redraw the picture down here. So let's suppose I made my guess here, x1. I drew my tangent line. That gave me this value x2. Now what I'm going to do is I'm going to do the same thing, and I'm going to go down, and I'm going to draw the tangent line here. So maybe let's use a different color for this. So I'm going to use the tangent draw the tangent line here. And this point where it intersects there, that will be our next one, so that will be x3. And then we just continue to do this, and you can see each time here, we're getting a little bit closer. And if we do the same, go through the same calculation, the tangent line, the green tangent line now, x2, f of x2, well, just like above, this is going to be y minus f of x2 as f prime of x2, x minus x2. And now to find our next guess, so to get x3, well, that's going to be where the y is equal to 0. So I have 0 minus f of x2 equals f prime of x2, x3 minus x2. And if we solve this for x3, we get, this is a 2, x2 minus f of x2 over f prime of x2. And what's important to notice here is this is the exact same formula as we had above. We've just moved along to the second term. So that's what we mean by iterating this, is we have a formula now. So I can say if I have calculated n of these, the next one is given by this formula. So for instance, x5 would be x4 minus f of x4 over f prime of x4. So you can keep calculating these further and further out and get better and better approximations. So that's how Newton's method works. Let's do a couple of examples, and then we'll see how to implement this with Mathematica. Things like this are nice to do by hand, but often when you're trying to iterate something to get better and better approximations, the computer can do that much better than we can. But it's good to see one by hand so we see how it's working. So sometimes you'll be given the initial guess. Sometimes you might have to look at the graph to get an initial guess, or you could use intermediate value theorem and figure out a value where it's positive, where it's negative, and just guess something in between. But we're going to do our initial guess with 1. Okay, and let's approximate to x3. So just do a couple of these. So first we calculate f prime of x. So this is 3x squared plus 2. So that means if I look at x2, this is x1 minus f of x1 over f prime of x1. So since we've taken this to be 1, this is my x2. And now I just want to fill these values in. So this is 1 cubed plus 2 times 1 minus 4 over 3 times 1 squared plus 2. So this is 1 minus 1 over 5. So this is 6/5. So that's my first value of the iteration. And now we wanted to do one more because we wanted to get x3. So this is going to be x2 minus f of x2 over f prime of x2. So notice to calculate x3, we have to calculate x2 first. We can't go directly from x1. So this is then 6/5 minus f of 6/5 over f prime of 6/5. And if we fill that in, that's approximately 1.17975. Okay, and we'll come back and see how to do this in a minute with Mathematica. So let's try one more example by hand. So let's approximate 5th root of 20 to x3. And then we'll use Mathematica to approximate to 8 decimal digits of accuracy. So we'll see how to use Mathematica after we do the first couple by hand. So for this one, we need to figure out a function. So what we could do is we could say, if I look at f of x being x to the 5th minus 20, notice that f of 5th root of 20 would be 5th root of 20 to the 5th minus 20, which is 0. So really what we're trying to do is we want to approximate a root of this function. So sometimes we have to change things into something working with functions. We had to do this when we were doing Taylor polynomials as well. So now I could guess here, if I took, say, x equals 2, I would have 2 to the 5th. So that's, I mean, it's not great, but it's not terrible. So let's just start with that. Just for something different as well, notice that f prime of x is 5x to the 4th. So x2 is going to be 2 minus f of 2 over f prime of 2. And so this is 2 minus, and then I'm going to have 2 to the 5th minus 20 over 5 times 2 to the 4th. Now 2 to the 5th is going to be 32. So this is going to be 2 minus 12. And then I've got 2 to the 4th is 16 times 5. So this is 16 times 5. We can simplify this a little bit by hand. So we know 4 divides the top. So I could write the top here as 3 times 4, and the bottom is 4 times 4 times 5. So this is 3 over 20. So this is 40 over 20 minus 3 over 20. So this is 37 over 20. And then we would just do the same thing for x3. We'll plug in the values but not get decimal approximations for them. Okay, my pen doesn't want to work now. Okay, so my pen seems to stop working, so let's go ahead and just switch to Mathematica to see how we do that for these. Okay, so now we'll see how to use Newton's method using Mathematica. So first, let's go ahead and define our function that we were working with. So we're going to do this with an f brackets x underscore, and we're going to say x to the 5th minus 20. And then we hit Shift-Enter to enter this. And then we can just, for example, just to make sure it works, let's plug in a value. So plug in 1. And we get minus 19 as we would expect. Now let's go ahead and define our iteration function. So this is x minus f of x divided by f prime of x. And now we can plug in, we said that 2 is our initial guess, so we could plug that in. And we see we get 37 over 20. We could iterate this a couple of times. And that would have been our next one, so that would be x3. Of course, there's a better way to do this, so let's go ahead and make a list. We'll call it L. So we'll do nest list. You don't have to worry about memorizing all these commands. It's just useful, so you can just copy these if you'd like. So we'll do, so n is the function we're going to use. We're going to start our initial guess at 2, and let's do 10 iterations. And now if we want a particular piece of this, we can do, let's put an n, so the n is numerical, just so we get just the decimal approximation. And let's do L, and let's do the 7th one. And we get 1.82056. And now if we want to do a bunch of these at once, we can loop through and get all of them. So we'll start when k is 0. We'll do k less than 10. We're going to increment k by 1 each time, and now we're going to print our list. And this is going to be we're going to set the precision so we can make this a little bit more precise, so we get more decimal places if we like, and then we'll use the same command, except for now we're going to go the kth one because we're going to run through the k, and let's do 25 digits of precision. And see, here is our list for this. So you can see this is a much faster way to do this, and you can get, we also had our 8 digits of precision, so you can read that off of this as well. So as long as it's not changing, as you keep going down, then that's accurate for that far. So that's how we would do this for approximating the fifth root of 20. So let's look at another example, though. Let's maybe put the text in here. So let's insert some text. So let's estimate the value of x where, say, sine of x is equal to x raised to the 2. So again, this isn't looking like something where we're looking for a root, but what we can do here is we can define our function. So let's say f of x, and now these two things are equal when the following function is equal to 0. So let's say sine of x minus x raised to the 2. And so when that's equal to 0, sine of x is equal to x squared. So let's use that. And then we'll define our iterated function again to be x minus f of x divided by f prime of x. And now we can pick whatever value we want for our guess. So let's start that with 1. So for instance, if I did n of 1, this is going to, maybe we want to do a numerical approximation for this. So let's do n of 1. There we go. So see, you get the, if you put the semicolon after it, it suppresses the output. You got to remember that. But notice this isn't really giving us something so great because it gives the exact value. So if we want a numerical approximation, we can put that capital N around it. And then we see this is about 0.891. And of course, we could do several of these just like above. And that gets us a little bit better approximation. But just like we did above, let's go ahead and do a list. And so again, we'll use n. We started with 1, and again, we'll use 10. And then we can go ahead and copy this command, so we don't have to type the whole thing in again. Put that down here. And then we see there's our list there. So you can see it stays the same actually all the way across here. So this converges. So you can see this converges very quickly. In under 10 iterations, we're already getting all of these decimal digits of accuracy. So that's how you can use Mathematica to use Newton's method. It's much easier and faster than doing by inputting them by hand over and over again.